In this video, we'll be talking about standard oxygen sensors. Now, what we deem a standard oxygen sensor, the one that has been around for a long time now, really there are two main types. There's a Zirconia sensor and a Titania sensor. Do you really need to know how they're both built? I don't think that's that important for our discussion. You need to know they both exist. They're a little different. They're not interchangeable. Now, the Titania was really only used for a few years. I don't know anyone that's currently using it. And so we're not going to talk about that one. Just know some older Nissans used it, some Jags used it, a few other cars used it, but wasn't in widespread use. The Zirconia, now that one was actually very common, still is. You still find it in cars today. In fact, pretty much every post-cat oxygen sensor is still a standard Zirconia O2 sensor, even if it has wide range or wideband sensors pre-catalyst. Now, the Zirconia sensor, it actually acts a lot like a battery and those of you that like to be technically correct will call me out on this, but we're just going to say that it creates its own voltage. And it does this through a catalytic reaction inside the sensor itself. It's a difference in oxygen. Now, it also needs some hydrocarbons to make this happen. That's why I say it's a catalytic reaction. You need some hydrocarbons and some oxygen. And it samples that oxygen. It samples the difference in the oxygen inside the exhaust stream and outside of the exhaust stream. If we happen to have low oxygen in the exhaust stream, especially relative to atmosphere, which is 21% O2, for those keeping track. If we have a high oxygen content outside and a low oxygen content inside the exhaust pipe, we have a great differential. Okay, first off, why would we have low O2 inside the exhaust? Because we had more fuel than air. We used all the air up trying to take care of the fuel, a rich condition. So we have low O2, a rich condition. That means we have a high differential in the oxygen inside and outside of the exhaust pipe. That's going to create a relatively high voltage from the sensor. This sensor produces 0 to 1 volt. If we have a very rich condition, we're going to be up close to 1 volt. Now, on the flip side of that, if we have high oxygen in the exhaust pipe, like close to 21%, okay, it doesn't have to be that high, but if the differential is not as great, if we have high oxygen inside the exhaust pipe, high oxygen outside the exhaust pipe, then it's fairly neutral or balanced out, then we're going to have a low voltage output from the oxygen sensor or close to 0 volts. Now, really what we might consider the oxygen sensor is a stoichiometric switch. Now, stoichiometry, we'll keep it with the automotive version. That's when we have the right amount of 2 or more substances that are going to give us complete combustion. So in our case, if we're talking gasoline has a stoichiometric air-fuel ratio of 14.7 to 1. So if we have 14.7 parts air and 1 part fuel inside that cylinder, under the right conditions, theoretically, it should burn completely. Consume, but that's not proper. It's going to rearrange everything because the whole conversion of matter, right? But it's essentially going to consume all of our oxygen and hydrocarbons, i.e. gasoline, in the process. Now that's in a theoretical perfect world, which we don't live in. But that's for you to know, is that if we talk about stoichiometric air-fuel ratios, we mean one where we have the exact correct amount of fuel and air to give us a theoretical perfect burn. Now, in our standard oxygen sensor, if we are at a stoichiometric air-fuel ratio, or our correct amount, that sensor will sit at about 450 millivolts, or just about exactly halfway in its range. But that sensor isn't built to work like that. It's built to switch continuously. It can't just sit at 450 millivolts. It won't work. It would keep wandering up and down. So what we do is we force it to switch. And we do it very rapidly. And what we're looking for is for that switch to go to at least 700 millivolts and then drop down to 300 millivolts and back up to 7 and back down to 300. It can go a little higher, it can go a little lower. But as long as it's switching up and down, up and down, up and down continuously, then that's going to average 450 millivolts, and we will be right about a stoichiometric air-fuel ratio. Now, that switching has to be even. So even if we go up to 800 millivolts, if we stay up there for a long time, then come down and only spend a split second down at 150 millivolts, and we shoot back up and hang out for a long time at 800 or 700 or 950, that air-fuel ratio is going to average rich. So what we need to do is make sure that we are even in our switching up and down. Now, I said that 450 millivolts was technically our stoichiometric break-even point, right where we want to be. What's important in our standard O2 sensor is once we get above 450 millivolts, how rich is it? I don't know. It's richer than a stoichiometric air-fuel ratio, meaning we have less air, more fuel than we theoretically need. Below 450 millivolts, now we have too lean of a condition. How lean is it? I don't know. It could be 15 to 1, could be 17 to 1, could be 27 to 1. I don't know. We just know that anything less than 450 millivolts means that we are in a lean condition or leaner than stoichiometric. Our whole goal of the sensor is to switch above and below that 450 millivolts constantly and consistently when we're in closed loop operation. So why don't we take a look at an example of that on the scan tool and the oscilloscope, and you can kind of see what I mean. So we'll look at that and come back to this in a second. We're going to start with a scan tool capture here. This is scan tool data that was taken during a road test, and this vehicle is just being driven pretty normally at this point in time. Now, first and foremost, the thing about looking at an O2 sensor on a scan tool is that O2 sensors are an analog and relatively slow signal. So if we're just trying to make some relative measurements and some relative inspection, you'll actually find that the scan tool is perfectly acceptable for doing this for a lot of cases until we actually have to get into some more precision measurement. And what we can see going on here is that if you look, here's our voltage on the left side, and you'll notice that this sensor actually got as low as 61 millivolts. That was its lowest at the bottom. It usually averages, probably around 80 or so on the low side. Switches up to the high side, and we're clearing 800, going about 820 or so. It hit a peak of 833. So this is pretty normal. You can see that we switch quite often. Here's 450 is going to be right through about the center of this. So we have some good switching. It's fairly consistent. It's really a pretty normal looking O2 sensor as far as scan data goes. Now I'm going to throw out one caveat here. This is a snap-on capture, and like a lot of scan tools, where normally we would have time on our other axis here, on our horizontal axis, what you see here, these numbers, these are actually frames of data. So don't try and use this on a scan tool, this horizontal axis. Don't try and use this as a time axis. Now let's go ahead and take a look at a scope capture. So here we're looking at a lab scope capture of our same oxygen sensor pattern. Now you'll notice that it really doesn't look that much different than it did on our scan tool. The biggest difference being is we've recorded a lot more data points. So now if we want to zoom into this in a little bit, and we will, you'll be able to see a whole lot more detail. We can't do that on the scan tool. We can only get a picture about like this, maybe a little bit finer, but not much. But right here you see we have some good even switching. If I take one of my cursors and I run it right about through the rough middle of that, I am right about 437, 438 millivolts. We're looking for 450, and I pretty much guessed it there. So that looks pretty good. It looks pretty centered. We're doing okay. If we measure across the top, kind of an average there, and we'll go ahead and measure across the bottom, you'll see that our scope caught this switching. It dropped to about 73 millivolts on the low side, about 833 on the high side. That's doing pretty good. This is a decently working sensor. So now that we've taken a look at our scope and scan tool captures, now we're going to dig back in real quick. We're going to look back at a scope capture, and what I want to show you is the transition time. When that sensor is truly working, as it should be, we want that transition from low to high, or high to low, so that roughly 300 to 700, if we were really good, 200 to 800, but at least at 300 to 700 millivolts, we want to see it make that rise in less than 100 milliseconds. And the same thing on the fall on the other side. We want to see it drop from 700 to 800 millivolts down to 200 or 300 millivolts in under 100 milliseconds. That means that our sensor is working okay. Now, the sensor can switch much more slowly than that on a good working sensor if the computer is causing it to happen. So be cautious here. If you have a sensor that you're unsure about and you're testing it with an oscilloscope, don't just call it bad because you saw it switch at that rate. Make sure it's fully warm, which we'll talk about in a couple minutes, and make sure that you forced it to switch as fast as it can. So add a whole bunch of fuel in a hurry, snap the throttle open, yank a vacuum line, do something to force it to work quickly, and then measure the results. There were a lot of older Asian cars that switched very slowly at an idle, and that was normal. That's just how they worked. The sensor was fine. There was nothing wrong with it. So again, we'll look at it, and you're going to see that a good sensor should make that transition in under 100 milliseconds. All right, so check that out. I'm going to zoom in on just one switch, roughly. And I've already set up the cursors to measure this out. Now, I prefer to measure 200 to 800 millivolts. So actually, I do have to tweak this just a little bit. So if I take this lower cursor, and I'm going to set it right at 200 millivolts. You can run this 300 to 700. I really prefer 2 to 8. And I can't quite make 800 on the top, so I'm just going to put it at the upper part of the switch right here, right when it pretty much topped out. So I'm at 200 here. I am at almost 800 on the top. Now I'm going to bring my time cursors over, and I'm going to set them up so that they intersect. So my number one's right here. It intersects that 200 millivolt mark. My second is going to go right here. It's going to intersect that almost 800 millivolt mark. And I'm going to look at my delta time between the two. That's in this box right here. And I'm going to see that that delta time is just under 50 milliseconds. I needed to be less than 100. I hit it at 50. I'm pretty good. So this is the rise. Now let's see what the fall looks like. And again, we also want that to be in less than 100 milliseconds. Let's see here. I need to unlock those. So we're going to move that one over there. So once again, you see this intersects in the waveform right there. We've intersected the 200 millivolt line there. I'm intersecting the roughly 800 millivolt line there. And on the fall, this occurred in about 64 milliseconds. So that's pretty good. We are well under our 100 milliseconds. Realistically, let me back up one. A good sensor should be able to do one of those switches, either lean to rich going up or rich to lean going down in about 35 milliseconds. That's what a true good sensor should be. Now, it's worth noting that I wasn't forcing this sensor right here. This vehicle was just held at a higher RPM, so it was switching normally at this point in time. If we are concerned about a sensor, or if it's anywhere near its 100 milliseconds or slightly over, then we really need to make it a point to force the sensor. We need to force it rich and force it lean rapidly, like snapping the throttle and then suddenly letting off, and then going back and measuring at that point in time how fast our reaction was. All right, so now that we've seen the rise in the fall time, the important thing, and I mentioned it a little bit ago, it has to be hot to work properly. Cold O2 sensor doesn't work. Our oxygen sensor starts to work at right around 600 degrees Fahrenheit. Its optimum temperature is about 1500 degrees Fahrenheit. So we have to get that sensor good and warm to work properly. Modern sensors are all heated now. We have 1, 2, 3, or 4 wire sensors going back from when they started out. The original 1 wire sensor was not heated. It required the heat of the exhaust system to warm it up enough to make it work. It usually was not a quick operating sensor. It didn't have real fast switching. The computers didn't need it at the time. It was good enough. Next we went to a 2 wire sensor, which is really just a 1 wire sensor with an additional ground back through the ECM or PCM. Then we go to a 3 wire sensor. Now we have our signal wire, we have a ground, usually for the heater at this point, and we have a heating element built into the sensor itself. And for the last, 20, 30 years, okay, maybe not quite that long, at least solid 20 years or longer, now we've had 4 wire sensors. So now our sensor has a sensor wire, a sensor ground. We also have a heater, power feed, and ground. And that's the most common sensor you're going to see now is the 4 wire sensor. We have to get that sensor hot. We have to make it work. There's no way we can pass emissions without it. The other thing too though is when we first started getting 4 wire sensors, when you turned the car on, they would get a power, they were grounded. Usually the ground was solid and they're grounded through the body of the sensor. So you'd power the car up, it would have its ground, it would just come on, heat up the sensor and be working. Newer sensors, newer technology, now we know that once we get it warm, that's a waste of power. Not only that, there are operating modes where the exhaust may be generating enough heat to keep the sensor working anyway. So now you'll find different strategies depending on the auto manufacturer, but there will be a lot of O2 heaters that are now pulse width modulated on the heater side. So they're going to control it. They may give it a really high pulse width when it's cold to bring it up to temperature in a hurry. And then once they actually get it heated up and it seems to be working normally, switching fine, they'll back the pulse width off to maintain just enough current through the heater to keep it at a good operating temperature without wasting power. The really important part about that one is that sometimes they may even turn that off. Again, if they think there's enough heat in the exhaust stream to make it work, they may even turn off the pulse width to the heater and just let the heat of the exhaust do the work. Just remember, if you're looking at scan data and you see sensors do something you think is funny, like shut off a pulse width, turn off a heater, but you have no codes and you don't really have any problems with that sensor, that's usually a normal operation. So let's take a quick look at a little bit of scan data, something you might see if you are actually checking out one of these sensors. What we're looking at side by side right here, on the left, you're looking at a picoscope capture of the circuit for the O2 sensor heater. On the right, we have a scan tool capture showing us that same circuit, or at least what the scan tool is able to show us from what the PCM is telling it. Now there's much more time on the scan tool capture than there's in the scope capture, so I'm going to scroll the scope capture along. But right here you think it doesn't really look like much, but what it really is showing us is it's holding that sensor to ground. So I'm on the triggered or ground side of the heater, or the heater circuit for that sensor. It's holding it low, so this is a 100% duty cycle. It's got power applied to the other side, it's fully grounded on this side, it's flowing full power. That's what you're seeing when it turned on. Right in here, you're seeing it ramp up and hold that power. But now, once the heater starts to warm up and it doesn't need as much power, as much amperage to maintain itself and to keep it working properly, you're going to see the amperage, that's what's represented in the scan tool capture over here on our vertical scale. The amperage is going to drop over time. To do that, if we look at the circuit through the lab scope, it's going to start duty cycling it. It's going to start pulling it off ground and giving it a little time where there's no power flowing in the circuit. So every time it comes off ground, that's actually depowering the circuit because we had power applied to the other wire. So as you see it duty cycle on our scope capture here on the ground side of that sensor, that's the same spot where our amperage is dropping off all the way through here till it drops down about 450 milliamps and kind of hangs out there. They're going to do this so that the sensor has just enough power to stay at its operating temperature, but not so much that we're wasting energy. We don't need to overheat it. The exhaust stream will help keep it heated up, and we're going to duty cycle it to just maintain that temperature and do it at the optimal power supply. So this is kind of what you'd see on a later model O2 heater that's pulse width modulated. That's what's going on right here. That's our pulse width modulation. Okay, the last thing I'm going to leave you with, some removal and installation. First off, we have a lot of special tools that we can use for getting oxygen sensors out, and where they're located a lot of the times, these are a good thing. Sometimes they're super simple. You put a 22 millimeter or 7/8 wrench on it, crank it right out. Other times we need some specialty sockets to get in there. My warning to you, this sensor is in the exhaust system. This sensor has lived in that exhaust system for 60, 80, 150, 200,000 miles. There are many times when the threads of that sensor become galled or seized into the exhaust pipe. So at the very least, we may have to get the torch out and heat that sensor up dramatically in order for it to break loose and remove it so we can replace it. Now, when we have to do that, usually the threads are damaged as well. Most of the time that's fixable, but we have to be very cautious, tap that back out, clean it up before we even attempt to put the new sensor in. If the threads are damaged, don't just try and jam a new sensor in. All you'll do is damage the threads on the new sensor. Also, when it comes time to put the new sensor in, they come with a little tube of anti-seize in the package of almost every oxygen sensor you buy. There's a reason for that. Use anti-seize on the threads of the sensor when you install it. That'll help, hopefully, keep it from galling in that exhaust pipe. So maybe if it has to get changed again in the near future, it'll come out more normally. And with that, we'll catch you in the next video.